Yes, I'm going to speak about something slightly unusual because it's very interdisciplinary. I'm trying to use tools from biology such that we can learn something about the evolution of the Milky Way. And because this is an astronomy audience, I thought that this is going to be probably good if we go through some biology concepts first. And of course, my screen is not reacting. I'll stop sharing. Oops. And I'll share again. Wait a second. Zoom. I'll share my desktop. Apparently that works better. How do I share my, here. Okay, so now we are all probably seeing Emily. Okay, now it works. Okay, so let's go through some concepts because I want to try to put this idea on your head that we can do this, because I'm very convinced we can do this, and it's kind of complicated. So that's why I want to go through the concepts. So I'm going to take some quotes that I've been taking from these 3 different books that I've been reading through the pandemic. All of them have been very illuminating. The first one is a professor actually at ANU in Australia. Phylogenies are actually a way of organizing ideas about evolution, and not about human living beings, but it's about how do we organize our ideas about evolution. And this is not working again. This is annoying. Sorry. Let's try one more time. If not, I'll have to go probably without this. Okay, so they are these diagrams which help to display relationships, and that means that lineages, which would be one of these quantities here, that are more closely related to each other will be more closely related in a phylogeny. And this is because they share a more common recent ancestor, which
Sorry, we can't see your slides.
You cannot see my slides.
No, I think you didn't reshare.
Sorry, this is...
No worries.
Obviously, when you think to speak and you're kind of in YouTube live, then this is all then it doesn't work.
Now we can see it. Perfect.
Yeah, okay. So let's hope that this is the last time. If not, I'm going to not make this full screen mode. Okay, so these phylogenies, the idea is that they help to display relationships. So lineages that are most closely related, they will be more closely related in a phylogeny. So they will be closer in the branches. And this is because they share a most common recent ancestor. In a way, this is behind chemical tagging. And actually, the paper of chemical tagging, or this review of chemical tagging of Ken Freeman and Joss, they kind of, in a way, said that. Phylogenies are also helping to record evolutionary past, because they connected past in these phylogenies. So in this here, they are, in a way, helping also to reconstruct the evolutionary history of this lineage. And this is, again, not working. Oh. This is a very bad way of starting a talk. And my computer freezes every time. So I'm not going to share screen. So my talk is going to be probably a bit more boring. We're here. Okay, so the idea of these phylogenies is that we can generate and we can test hypotheses about the different patterns and processes that will cause diversification. So it's a way of organizing why do we have diversification at the end. And it happens that in stars, we have actually a very diverse Milky Way. Stars are very diverse. So this is a plot here from Galah, from the solar twins. And you can see that there is a variety of chemical elements in all the stars, that in some cases it also changes with ages. And the diversification of all the stars is because of a combination of different things like supernovas, inflow, outflow of gas, mixing of gas when there is a merger, and all sorts of things. So stars today, the stars that we observe today in the Milky Way are very diverse. And these results of some things that happened in the past. So phylogenies can be a very powerful tool to put together the trait evolution with evolution of entire systems. So that means that traits, this is a concept, a central concept in evolution, that the traits change over time. So phylogenies allow us to visualize the history of trait evolution and discover these patterns. And important here is that actually trace allows us to reconstruct evolutionary changes that occur of any kind of trait. So you don't need a mom and a dad, you just have any kind of trait to study phylogenies in this way. You can do it with languages, you can do it with religions, you can do it with many different ways. So you don't need to think necessarily about biology entities or living entities on the planet. And another thing that I think that is very important is that traits can constantly accumulate change in time, but the rate of change can vary. So, and the variation I think that is very important because in our case, this is where we have the physics. So this is a boring talk because all these things were kind of coming out and it was easier for me. So the question that we need to make ourselves then, if we want to do this in the galaxy, is which traits are we going to find that are evolving with time? So here there is a plot, or two plots together from a recent paper from Paul Nissen, where there is one abundance ratio, yttrium over magnesium as a function of age, and then there is another abundance ratio, chromium over iron as a function of age. And here, this is a classical Tumbre diagram, velocities of many stars. And this is important because when we want to make phylogenies, we need to be able to distinguish between evolution traits that are changing with time because they are produced by descent, than traits that are evolving independently. So those that are driven by descent are those that are going to help us in covering the evolutionary relationships that we have. So in this case, a trait like this that evolves with time and that shows that there is a change in time is going to be a useful trait for us, while a trait like this, in which the velocities are actually a mere coincidence because one star is not going to inherit the velocity of the other per se, it's not encoded in there as a kind of intrinsic property, is not going to be a trait that is going to help us to uncover evolutionary relationships in a phylogeny. And then I put a question mark here because chromium over iron, for example, has a very weak dependency with time, which means that it is not necessarily something that is evolving with enough signal for us to really find relationships in an evolutionary context. And in choosing what traits to compare, which is called in a way in biology alignment, is one of the most important parts of any evolutionary analysis. So if one chooses the wrong traits, you can lead to false conclusions. And this is in a way similar also to strong chemical tagging and to all the discussions we're having in this meeting about which elements are we going to choose, what is the chemical dimension, what are the nucleosyntheses that are different from each other, to which uncertainties can we really start finding this evolution with time. So phylogenies then, they are a way of representing possible evolutionary histories. So grouping then should be done on the similarity that is done by descent and not by these incidental similarities, as I said before. And descent modification will then create a hierarchy of similarities in a way that close relatives will be more similar in many other aspects. And I want to stress here that phylogenies represent possible evolutionary histories. So there may be many histories that may explain the present data. So one can and one should then try to see how robust the different interpretations of the data may be. So can we apply this tree thinking in chemical evolution studies? Yes, we can, because we have some change that is done because of descent. We have some traits that are inherited in chemical evolution, and these are the stellar abundances. So we can collapse this information into a phylogenetic tree and like this create a phylogeny and try to reconstruct history in this way. So we have done that already twice with very dedicated small set of stars. This is the second work we did, which we did with an undergrad student from the MIT that came to visit me when we could still travel, and with a student from actually that is now also in Australia from biology, and with some other colleagues that you may recognize the names. So we published that work early this year. And I'll introduce you a little bit what we did in that work. So we used, again, a sample of solar twins. The sample is this Bedell data set, so it's 80 stars. that I have quite a lot of measurements of abundances, 30 of them, and the stars cover a wide range of ages. And the data is beautiful. It's HARPS data, very high signal to noise, and everything is done, calculated with differential analysis. So precision is absolutely perfect. And this is for us kind of a great data set to start with. So then to select the traits, we want to have traits that are evolutionary informative. So I will not go much detail into this because there is a talk after about Fran Espinosa who can explain a little bit more about these kind of traits. But putting them in the tree, we can get this kind of tree. So this is a similarity tree. The idea is that we compare the chemical abundances of all these traits among all the stars. We calculate a distance matrix, which will tell the difference among all the stars, and this is displayed in this kind of tree. So this tree is not like the typical tree, like the one that I showed initially with a root and then a branching pattern, because we don't have a root here, because we don't know what comes first. In this particular case, we have no model. This is completely empirical, everything. So the tree is not rooted, but there is still an evolutionary direction in a way, because the old stars which are here are clustered together, and the young stars which are here are also clustered together. So the youngest stars and the oldest stars are most different to each other in this tree. And the other interesting thing is that there are some anomalies in the tree. So you can see that there is a kind of clusters of stars here, many of them kind of messing in this point and another one here. So they are not evenly distributed in the tree. And this is also something that can tell us something about the past. There were maybe some events that caused this kind of features in the tree. So we can turn this tree around, which was supposed to be here with a beautiful simulation, which you're not going to see, or not simulation, but some effects. And it is now seen in this corner here, and we can now display the tree in a more classical way, where that part of the tree is now kind of extended here, and this branch here is that one, and then that whole branch here is that branch here. And we can color code the stars according to where they are located in the tree and see what the abundances are doing. So we see that the blue star alpha enhanced, the yellow stars have actually quite a very small dispersion in their abundances, and the red stars are, for example, enhanced in these process elements. We can also see a bit what the dynamics or what the kinematics of the stars are doing. We didn't put that obviously in the tree, but now we can use the kinematics because we have it, and like this we can interpret our data a bit better. And we can find these blue stars here are kinematically hot and old. We can see that the yellow stars actually cover a wide range in birth radii. So one could think that because they are so homogeneous in chemical abundances, they may be coming from a cluster. And in that case, we may expect them to come all from the same region, but actually it is not very well seen here, but there is a yellow line here that shows that these stars are kind of covering a wide range in birth radii. And finally, the red stars are kinematically quite cold and they are young. So with these things, we know from the literature that this make and the other point is also the trees imbalance. This is interesting in biology because tell us that only one of these lineages is kind of evolving until today, which is this one here. So with these things in mind, I don't have it in this, we can interpret this branch here as the thin disk because of all these properties together. These stars here, because the origins of these stars are essentially across the galaxy, we can call them a burst, and these stars here is the thick disk. If we turn the tree again to the opposite, we make it small, and then we display again our previous tree. So then we know, sorry, I'm going to put it out. We know that, again, how we call these stars, this is the thin disk, the burst, and the thick disk. So the thick disk would be this one, the burst would be this one, and the thin disk would be this one. We can now tell a story about the shared history about these stars. So we can tell that the thick disk is an ancestral population of the thin disk because of the directional evolution here. And the kinematics are hot because of probably, a merger with Enceladus. We can then think that the burst stars are a product of star formation enhancement caused by the merger of Enceladus in the thin disk. And then after this burst happened, we can then have the typical evolution of the Milky Way, of the thin disk. Again, I put this back. There are many stories that can explain the present data. In the paper, we had other stories as well. I just put this story here, but there may be other stories that could also explain this data. So to conclude about this, this is not a new result because we are not discovering anything new, but it's very interesting to see how with this combination of elements with only 80 stars, but using phylogenetic trees in a way to interpret the story behind these stars, we can tell a story that we can also know from other independent analyses which use very large data sets. And here I just put also something that I like very much, again, from these different books that I was reading to put this information for you here, is that we can do a lot of progress with a mixture of empirism, intuition, and a formal theory. And I think that this is what we're trying to do here with these phylogenetic studies.
Pelle, you have 5 minutes remaining.
Okay, so let's now think of doing this exercise on Gala data. Because with Gala data, we have a lot of data, and because it's a conference where everyone wants to know what kind of things we can do with Gala. So we have doing like Keith over the weekend and the last week trying to put some plots together about trees in Gala data. So we start again with taller twins. This has been done mostly by Keegan, who is this biology PhD student who came with me when he came to visit in Chile, then to Las Campanas actually, and he was, I don't know if he was more excited about the stars or the animals, but he was very interested in the foxes and donkeys of LCO. So this is a picture of him looking into animals. And here is the sample we have. So we tried to select again solar twins based on the temperature and log G and metallicity, because like this we can just understand the differences between what we did before on solar twins and here by just changing essentially the data quality and the method of analyzing the data. So we have about 10,000 solar twins. And the first thing, the first challenge we find is that there are gaps in the chemical data in the sense that not every element is measured for every star. And that is something that we haven't accounted before. So we have to think on how we're going to compare similarities and differences if we have empty data. So, but by the moment selecting only stars that had all the abundances measured and trying to find the traits that we were using before in this Jackson's work, and concentrating on the same volume that we had before, which was extremely local, we have 85 stars that have all the measurements, and we have 23 traits in common. And this is the volume that we started looking. This is just for the sake of this making a plot about trees here. But important here is to see also the age, the range in the uncertainty. So the Bedell data set has an uncertainty that is ridiculously small. It's so small, it's beautiful, while real survey data have uncertainties that are larger. Anyway, the trees would look like that. So this tree here is the tree of the data we had before, but now not using all the traits, but only the traits in common. And this tree here is a tree of the Gala data of the same volume that we had before and solar twins. The scales of the branch lengths are not the same. This is kind of scaled in this plot, so don't think about the length of the branch lengths. But what is interesting is that we, in both cases, see this imbalanced tree. So there is an indication of a thin disk evolving with time in both cases, which is encouraging. But then the other part of the tree, kind of the inner part of it, where we had before all stars and our bursts and everything, here it's all much more messy. And we can make a statistical test on understanding how robust our nodes are, kind of, and this is shown here in these pie charts. So the nodes tell us how blue is kind of the percentage of how many times this node appeared in a Monte Carlo simulation in which the trees are calculated considering the uncertainties in the measurements. So you can calculate different differences in the chemistry according to the chemistry. And in the previous case, when we had the previous data set of the solar twins that are measured with very high precision from HABS data, we had an overall very good support of above 50% in the clades. While now in the Gala data set, we have a very poor support. Actually, it's much below 50%. So before we conclude on anything, this is again very preliminary, We have to select better the traits. We have to deal with better uncertainties in a way. And I think that there are ways to improve the uncertainties and to make better selections of this data. And this is kind of the things that we should be doing after this meeting. And I finish here with no conclusion, but some thoughts, and saying that this meeting is very helpful for understanding more the GALA data, which for this kind of study is very crucial. So I'm very excited to have the opportunity here to talk to all of you and to learn about the GALA data in general. And yes, I feel a bit like that. Not necessarily more data implies solving all the problems. Sometimes more data means more problems and more thinking. So this is what we are going through now. And I just want to also finish here that if anyone is interested in coming to Chile for a postdoc, please contact me, because there are few opportunities coming in Chile right now. And I'm sorry for having to show this plot so small and no effects. Thank you.
Thank you so much, Paula. I'll clap for everybody. Thank you so much. It was very exciting, even though you didn't have your animation, still a very exciting talk. Are there any questions in the room? Perhaps we can start with questions in the room this time. I see we do have some questions in the chat, I think, from some people who are in the room. So we have from Tillman Hartwig asking, great talk and interesting new method. How exactly are the trees constructed? I guess you need to define some similarity measure between stars. If yes, how do you weight chemical information versus dynamical information?
Yeah, so again, the dynamical information is not in the tree, because I don't think the dynamical information is something that is inherited in stars. It happens to evolve by chance because the star was actually in, you know, a cloud that had that velocity, but it's not something inherited. While the chemical abundances are inherited, and they will be modified according to this theory of the Senford modification because of the nucleosynthesis yield. So that there is a physical reason of why we do see variation of the chemistry between generations. And this is the key concept of this inheritance that we can apply for phylogenetic studies. So dynamical information is not part there. And then, yes, how the trees are constructed. So we have this, we put essentially all the stars, and then we calculate the distance, the chemical distance, which is an Euclidean distance. So 1A minus B of the chemical abundances of each of them. So this is a matrix that calculates one with the other, so all the pairwise distances. And that pairwise distance, so the whole thing is about choosing the right abundances. We did in the paper, we present when you use normal abundances as a function of iron, the typical thing, and then when you start improving with these chemical clocks or the traits that are evolving with time that have been selected like that, and you can see how the tree starts kind of this resolving a little bit more the branching pattern when you choose different ones. But yeah, how to weight the chemical information and what to choose is very much an open question. We brutally now applied it in GALA, and the thing didn't really work. I think that yttrium and barium are still too uncertain, so there are work to do, and for that I need Sven and all the rest.
Very cool. It's been very cool in the first two talks to see science that happened over the weekend too. That's pretty thrilling. We have another question from Sarah Martel. First saying what an interesting way this is to look at abundances, but asking if you had more stars in the Bedell data set with the same quality, would you expect to get a more complex tree or more stars in the same structures?
Yeah, that's a very, very interesting question. And this is why we wanted to look at GALA. So I think that the interesting thing would be to see, and this is what we want to test actually, to see whether, for example, as we grow in volume, if we start finding more structures or more of the same, if we explore the inner part of the galaxy with the outer part of the galaxy, if we see kind of the branches having, you know, different amount of stars, and all these kind of things is what we wanted to do with the GALA data set, which essentially, if I would have the GALA data set with the level of accuracy and precision of the Bedell data set, that would be fantastic. but for that probably we have to wait a little bit more. And I want to comment that about what to expect. I think that in terms of the shape of the trees, we have to really work on making this exercise with models. So we are also working on that. We're creating chemical evolution models, and we're trying to create a framework in which we can account for what to expect, because actually from real data, you can never really know if two stars are going to be just siblings, and because of the uncertainties, they are just different and so on. So you don't really know from real data. But I think that the real data is the cool thing, because it's just real.